And somebody had pointed out to me yesterday, and another person a couple of days ago, that the order of the lessons is different. Like in your handout, we do 9.3 and then we do 9.2. And that's intentional. Incidentally, 9.2 is the final lesson in this unit. What that means is when we get back, the first day back, we will finish the unit. We'll have 2 days of review, and our exam will be the Thursday of the day we get back. That's going to give us, I believe, 4 days for year review before we write our in-class lowest exam, replacement exam. Catch my drift? Okay. Some of you call it a field test. It's not really a field test, but it's an in-class exam that we will use to replace your lowest exam mark. So we're getting very near the end here. And I think it's worth noting, just pausing for a second, most of you, all of you have come a long way. Long way. Like if you take a look at the work you're doing, the quality of math you're doing, and flip back in your binder to day 2 or day 3, and just take a look at the level of math that we were doing. It's changed, and so have you, which is a good thing. Today we're looking at quadratic inequalities in 2 variables. I feel as though I could have just taught this to you yesterday with linear inequalities in 2 variables. We're skipping over quadratic inequalities in 1 variable because it's complicated. Even though it's only 1 variable, it is very complicated. So we're going to be showing the solution to a quadratic inequality that has 2 variables graphically, with or without technology. And again, we're going to be talking about test points. So a little bit of an exercise for you to get your brain warmed up. I've got an inequality there which says y is less than x squared minus 2x minus 3. Can I get somebody to confirm that's the same inequality in your handout? Okay. So your job in the next couple of minutes is to go through and determine which, if any, of those inequalities make that, which, if any of those points, rather, make that inequality true. And if they do, I want you to circle the point. And if there's an ordered pair or a point that doesn't make it true, in other words, it makes it false, I want you to cross it off the list, and I'll give you a minute or 2 to do so. See how well I do. You can compare what I'm writing to you, what you've written. Incidentally, this is a little bit more complicated than what we were doing yesterday because you have that quadratic thing. So I'm basically putting in x, seeing what I get, and if the y coordinate is less, then I'm circling it. Would you agree 1 comma negative 4 is not making it true, but it's what I would call close? It's where they're equal. All right. I'm not really having a lot of luck here with finding points that make it true. By my count, I've got 3 points that make it true. Are any of those in dispute? Because I'm seeing a couple of you kind of going, oh, wait a minute. Is there one that you're wondering about? No? Okay. So it's only those 3. How many different ordered pairs exist that can make the inequality true? Well, let me approach this in a different manner than I did yesterday. If I were to take a point, let's say 8 comma something, can you do me a favor and calculate what the right-hand side of that inequality would be if I used x equals 8? So I'm going to take 8 squared minus 2 times 8 minus 3. I'm getting 45 as well. 45. So if I had this, is that a point that makes it true? No. But to get a point that makes it true, why don't I just use 8, comma 44? Because then y will be less than that. Or 8, comma negative 100. Or 8, comma 44.999. The point I'm making is I can come up with as many different y coordinates that will be less than that 45, making the inequality true. And the answer to the question is the same as the similar question's answer yesterday. The answer is there's an infinite number of solutions. And again, because it's a two-variable situation, for us to communicate what all of those are, pictorially is the only way to go, and we're going to have to do it in a two-dimensional space. One dimension showing us an x value and one dimension showing us a y value. Plot the graph using a dashed line. So what I guess I'm really asking us to do is to plot, I'm going to go to a clean slate here, is to plot x squared minus 2x minus 3 is equal to y. I think whenever we graph lines or curves or functions, we want to look at graphing the y equals. Okay? So now we have to do a little bit of a quadratic functions analysis. In order for you to get a good picture of this graph, you need to know the following things. You need to know the intercepts, and you should also determine the vertex. So the y-intercept is easy. Doing a bit of review here for your final exam, which is next month. The y-intercept is the constant term in a quadratic function. It's negative 3. To find x-intercepts, we're going to factor this. I'm going to explain to you why we factor it after we factor it. So what two numbers multiply to give negative 3 and add to give negative 2 would be negative 3 and 1, so it factors into x minus 3x plus 1. And I think that's elementary. But the reason why, this will be interesting, the reason why we factor it to determine x-intercepts is in order to determine x-intercepts, you let y equal 0. Now just look up here. Don't erase anything. Don't write anything else. To find x-intercepts, you let y equal 0. So you end up solving this quadratic equation, and then you say, oh, x minus 3 equals 0, x plus 1 equals 0, so you get x equals 3 and negative 1. Are you with me? But I think we've graduated to the point where we don't have to explicitly say that's equal to 0. Instead, we say the x-intercepts are always going to be the zeros of the factors of the function. If x minus 3 is a factor, then we will have an x-intercept at 3. This becomes important for Math 30 because if I say to you, what are the x-intercepts of this function? You don't need to write equals 0. You just say, well, one of the x-intercepts is negative 1, one of the x-intercepts is 4, one is negative 8, one is negative 1/2. Anyway, we've got our x-intercepts. Let's write them down. We have an x-intercept at 3, 0, an x-intercept at negative 1, 0, and then what we have to do is determine the location of the vertex. Those are the three primary things: x-intercepts, y-intercept, and vertex. And by the way, if there are no x-intercepts, then you should make a table of values to get a few more points. Otherwise, you've got a vertex, and that's it. So how do we do that? Well, we take the function y equals x squared minus 2x minus 3, and we prep it for completing the square. So we take the constant term, nudge it out of the way, and then what I'm going to do is add something in here to make this a perfect square. When you complete the square, and again, I'm taking this opportunity to review stuff. When you complete the square, your first step is not always to add that number. Sometimes you have to do something else. Why is it I will add that number as the first step here?
There's no coefficient with x?
Right. There is, but it's 1. Yeah, and that's what you mean. That the coefficient of x squared is 1, so we don't have to factor it out. We want a coefficient of 1 for x squared. So I take half of negative 2, which gives me negative 1, and I square the result, that gives me 1, which means I have to subtract 1 elsewhere. And I'm just going to subtract it over here. So this is the part that is going to be the x minus q quantity squared, and then we'll have the plus, pardon me, x minus p quantity squared, then we'll have the plus q. So we're going to get y equals x minus 1 squared. This number is always half of the coefficient of x. And then I have minus 4, which means the vertex is at 1, 4. And that's an awful important list of information. We can plot the vertex, we can plot the y-intercept, we can plot the x-intercepts, and we can get a really decent picture of the graph. Thank you for the funny look. It's 1, negative 4. I didn't mean you looked funny. It mean you looked at me funny, like I did something wrong. So the vertex is at 1, negative 4. Had I not seen that look and found that mistake, then I guarantee you that if I started to plot these points, I would know something is wrong. Because my x-intercepts, well, my y-intercept is negative 3. My x-intercepts are 3 and negative 1. And my vertex is 1, negative 4. Had I not noticed that I was getting kind of a sideways glance from some of you, and I tried to plot the vertex at 1, 4, I think the jig would have been up there. Like something would have twigged in my head and said, wait a minute, man, you made a mistake. So it is at 1, negative 4. So this is the series of points. We can add more points to this to help us sketch it better. For example, this will be a point because we know parabolas are symmetrical. So now when you sketch this, and again, I'm not that great at drawing on vertical surfaces, you might be able to do a better job, but I'm simply going to do that and that. And I'm not even going to go much further than that. I think that's good enough. And maybe tweak this a little bit. There we go. I don't know how precise this is. Like, for example, I see that on my graph, I have a point at 4, 5. I don't know if you put in 4 for x, if you're going to get 4, 5 or not.
Is this supposed to be a dash line?
And it will be dashed. I better erase it, yeah. I'm going to erase the little pieces. What do you get if you put 4 in for x? You do get 5.
Yeah.
Wow, I did a really good job drawing it. That's a fluke, right? I don't want to claim any credit for that. But yes, you are right. And jumping ahead here, why, Faisal, is it going to be a dashed line? I mean, you're told to sketch it with a dashed line, but why do you suppose that is?
Because it's not equal.
right? It's not equal to. And you remember that one point, there were probably others. I believe it was this point that I said wasn't making it true, but it was almost making it true. That's because it would be on that curve. So, yes, we need to make sure that when we sketch this, we are sketching it with a dashed line. And I know you get this, but let's plot the points. 4, 1. Well, 4, 1 is this point, and I believe it made it true, correct? We had circled that. 2, 2 did not. 1, negative 4 did not. 0, 2 did not. Negative 2, 3 I believe did not. 3, or did. Did negative 2, 3 make it true? It did, yeah. Of course it did. It's below the curve. 3, 2 did not. Negative 1, negative 4 did. And 0, negative 3 did not. So I believe, I just want to highlight these. I believe that these were the only 3 points that made it true. I mean, given everybody that we are working here on y is less than x squared minus x minus 2x minus 3, is anybody really surprised that the points that make it true are below the curve? Because it's y is less than. Bottom line here is, what do you notice about the ordered pairs which are part of the solution? They all lie below y equals x squared minus 2x minus 3. And I know for most of you, you're looking at this going, well, I'm not really learning anything new here. But it's an opportunity to review quadratic functions and how to graph them. So, how can all of the solutions be shown? Shade. Well, again, I don't choose to do this by actually shading. I just draw a bunch of lines. So that's the solution. You don't need to have the lines up top here in the top left corner, for example. We know what it's communicating. Why were we instructed to graph a line that was dashed? Because the inequality did not contain equals. So I'm just going to write this. There's a deeper reason, and it's that if you end up with having an inequality that does not say equals 2 in it, and you have 3 on the left and 3 on the right, 3 is not greater than 3, 3 is not less than 3, 3 is equal to 3, which means that pair of points that gave you that information would be on that curve. But since the not equal to, since the inequality does not include equal to, we can't have those points. And similarly, you could say less than or equal to or greater than or equal to means you have a solid line. I think that pretty much covers it. All right. So the solution to a quadratic inequality in 2 variables is indicated by a shaded region on one side, and by that I mean above or below. If it contains or equal to, then you use a solid line. If it does not, then you don't. You use the dash line. And you can either use what I taught you yesterday, which is that if it says y is less than, you shade below. If it says y is greater than, you shade above. Or you can use a test point. So we're going to run through just a few examples here. Sketch without technology the following inequalities. This is nice because we know the vertex right out of the gate. It's at 3, 1. It would be nice if we knew the x-intercepts. Are we okay with that? 3, 1. Okay. It would be nice if we knew the x-intercepts and the y-intercept. Again, even though it's not y equals, this will be important for, I was going to say tomorrow, but you know what I mean, when we return. Even though it doesn't say equals to, we're using this to decide what the curve will look like in the inequality. So what is your y-intercept? It's the result of changing x to 0. I think it's going to be off the charts here, isn't it? I think it's going to be negative 17. Thank you. So the y-intercept is at negative 17. Not a lot of help because we can't plot that point. The x-intercepts are where we let y equal 0. So let's rearrange this for x. I'm going to subtract 1 from both sides and get negative 1 equals negative 2 times x minus 3 quantity squared. I'm going to divide both sides by negative 2 and get a half equals x minus 3 quantity squared. I'm going to remind you that we're in Math 20-1, nearing the end of the course. No decimals allowed. I need to take the square root of both sides, and that's going to be plus or minus the square root. Then I can say that x is equal to 3 plus or minus the square root of 1/2, which is 3 plus or minus 1 over root 2. Square root of 1 is 1. What's the square root of 2? The square root of 2. We're not done. You have to rationalize that denominator. This is something we wouldn't have worried about way back when we did this math. But now that you know about that rule that denominators have to be rational, you have to do that. So what I end up with is x equals 3 plus or minus root 2 over 2. And we're not done because you need a common denominator. We don't like a number plus a fraction. You want to put these together. So I'm going to multiply the top and the bottom of that 3 over 1 by 2 to get 6 over 2. So our two x-intercepts are 6 plus or minus root 2 over 2, which is what you would have got if you expanded that thing out and used the quadratic formula. But this is not, when I say this is not that helpful, I don't mean to suggest that we didn't have to do it. I mean that we look at that and say, well, what are those x-intercepts? I can't look at this and tell you what 6 plus root 2 over 2 is. I can with a little bit of thought. It's going to be around 3.5, a little bit more than 3.5. But go ahead and take 6 plus the square root of 2. I want to say it's 3.6. 3 rounds to 3.7. Okay. So that's about 3.7. So if we go up here, we're going to have an x-intercept about here. Now I'm drawing it big so you can see it. It probably shouldn't be any surprise to you that the other x-intercept is going to be about here because it's a parabola. Right? But if I do take 6 minus the square root of 2, I get about 2.3 when I divide it by 2. And if you plot 2.3 on the x-axis, you get that. So it's not a very informative picture that we're getting here. It does make sense, though, that if the y-intercept is negative 17, this is a very narrow parabola. Here's what I would recommend. I wouldn't overdo it. I wouldn't even draw the parabola down here. I would simply draw this. Okay? I think that's good enough. If we were doing this on our calculator, we would probably want to change the window settings to bring out more features. How many of you would simply say, well, I did it again, didn't I? Solid line, it should be a dotted line because it doesn't contain the equals. How many of you would just say I'm going to shade below? Because it's y is less than, right? If it's y is less than, you shade below. And I think that's good enough. I think that communicates to us that it is shaded everywhere below. I realize that this shading continues down lower. But I didn't draw the graph down there, so there's no sense me adding the shading there. If that doesn't do it for you, then you pick a test point. And again, if the origin is open, if it's available, choose it. You put 0 in for x and 0 in for y, and you're going to get 0 is less than negative 17. And 0 is not less than negative 17. So that means that point is not a point, which means you shade on the other side of the line. Let's try one more. Graph this. Well, the vertex is at 4, negative 2. We're looking at this, and I'll have to remember not to draw a solid line because this also does not contain equals. Let's cut a few corners here. If I want to find the y-intercept, I put 0 in for x and I calculate y. And I believe you're going to get 14. So the y-intercept is 14. Not very helpful because 14 is not on the grid. It's on there, but it's just not on the part we're looking at. X-intercept, we let y equal 0. And start rearranging this. 2 equals x minus 4 quantity squared, plus or minus root 2 equals x minus 4. So the x-intercepts are 4 plus or minus root 2. Again, I don't think for this example we need to write everything down. I'm asking you to use your calculator to determine or to confirm that 4 plus root 2 is pretty close to 3.4 or to 5.4. And then you're going to take 4 minus root 2 and confirm that it's pretty close to 2.6. This is what the graph looks like. Oh, I almost draw solid again. It's almost easier to draw it solid and then use your eraser to get rid of it. And we're going to sketch the shading here that is above. Are you getting the drift here? I think we can dispense with the next one. I don't think we need to do another one like this. But if you were to sketch this very briefly, this is what it would look like. You would have an x-intercept at 5, an x-intercept at negative 1. You would have a vertex at 2, negative 9. You would have a y-intercept of negative 5. You would sketch the full curve with a solid line. trust me on those numbers, and you would shade above. I mean, that's what it's going to look like. If you want to take a minute and sketch it, you can, but I'm not going to show all the work to find those things. I will mention to you, though, that do you agree the hardest thing is to find the vertex? Probably. Once I knew, I want to go back in time here. Nothing to do with today's lesson. Once I knew those were the two x-intercepts, I knew the vertex had to have an x-coordinate of 2 because that's halfway between the x-intercepts. So then I took that 2 and put it into the equation and calculated -9. I didn't complete the square. I found the x-intercepts and looked halfway in between them. I know my parabola looks awfully pointy and it shouldn't be, but you get the drift, right? All right, we have one more example. The rope used by a mountain climber can safely support a mass m in pounds if it's modeled by this inequality where d is the diameter of the rope. What does this mean? Let's break this down. I have this inequality that says the mass must be less than or equal to 1,450 times d squared, where d is the diameter of the rope in inches. So let's imagine that we have a diameter equal to 1 inch. And let's just use m equals 1450 d squared. Or maybe we don't even need to do that. You know what I want you to do? I want you to calculate 1450 d squared if d is 1 inch. Man, I hope you don't need your calculator for that. It's 1450, right? So what this is saying is at 1 inch, the mass of the mountain climber in pounds has to be less than or equal to 1,450. I think if we went mountain climbing, we would all be safe, right? Because our mass is less than that. Why don't mountain climbers use rope that's 1 inch in diameter if it's safe for everybody? That's a lot of weight, isn't it? 1 inch rope is going to be very heavy rope to carry. So maybe you go, you know what? I want to go mountain climbing. Let's get that, you know what? Let's get that 1/8 of an inch rope. That's what 1/8 is in decimal. Look at that. They got a big spool of it at the back of Mountain Equipment Co-op. $20 for all that rope. Let's use that. Well, go ahead and figure out what 1450 d squared is now. It's not going to be 1450. Where'd my calculator go? There it is. Well, that's weird. It's going to be 1450 divided by 0.1 or times 0.125 squared. All right. 22.65. Who wants to join me? Nobody. Unless, you know, if Baby Yoda's mountain climbing, then maybe that's a different story, right? But the mass has to be less than that. If it isn't, it's not safe. And I think you understand why it's not safe. 1/8 of an inch is just not going to be able to withstand the strain. So what does the question ask? The question asks to graph the inequality and explain the meaning of it. We're going to do this on the graphing calculator. So we are going to sketch the graph on our graphing calculator. Of y is equal to 1450 x squared. We'll worry about the inequality aspect in a second, but let's graph that. Now, Zoom standard is not going to cut it. The first thing to note is that when we sketch this, we are not interested in any negative numbers. Right? Our x, which is actually d, has to start at 0 and be positive afterwards. How are we going to choose some settings here? Well, in my mind, I would do the following. I would go to my table. I'm going to do two things. And I'm going to change the independent to ask. And I'm going to go in here. And I'm going to put in a diameter of a rope that I feel is a reasonable size diameter that we probably wouldn't go past. I don't think you'd mountain climb with half-inch rope. Maybe. Half-inch is starting to get pretty thick and heavy. So I'm going to put in 0.5. And what I see is half-inch rope is more than sufficient, isn't it? If your weight in pounds is 362.5 pounds, you probably have other recreational activities that are more important than trying to climb a mountain. Okay? And I'm not trying to be funny, I'm being sincere here. That if that's your weight, unless you are some professional bodybuilder or something that is just absolutely bulked up, you have health problems and you need to exercise or you need to do other things. So 0.5 inches is more than enough. More than enough, right? But that tells me at 0.5 inches, y is 362.5. So when I go to my window setting, I can go from 0 to 0.5 and 0 to 350-ish. I'm not going to need to interpret that part of the graph because it's not reasonable. But I'm going to go to 350 up by 100. That just means it's going to put a tick every 100. And I'm going to, before I go graph, I'm going to go over and I'm going to shade below the line. Okay? So this is what the graph looks like. And I think I must not have entered my window settings correctly. 0.5 inches. I put 5. I knew I couldn't have entered them correctly because I knew 0.5 went to 362-ish, so I knew I should get something that fills up most of the screen. Quite frankly, I don't care what you sketch here. I'm talking about interpreting this and understanding what this means. What this means is that if I were to go to this particular point, whatever this is the maximum mass or weight. They're using M. This is the maximum weight that that particular diameter of rope can withstand. But let's pick a specific example. I'm going to go trace 0.25, which is 1/4 inch rope. Okay, so at 1/4 inch diameter rope, which is getting pretty thin, at 1/4 inch diameter rope, the maximum weight that it can withstand is 90 pounds. So would you agree, 90.6, would you agree that this is a point in the shaded region? Okay, well that point is 0.25 comma, I'm going to say 75 pounds. Would you agree? Ish. Is it in the solution region? Yes, because it's in the shaded region. Is it safe? Yes, because 75 pounds is less than that maximum of 90.625. It doesn't mean that all of these are solutions. It means every point in here is a solution. So if, for example, your weight in pounds, we can do something else here. Let's say that your weight in pounds is 180 pounds. Fairly tall person, fit, muscular, probably an adult, 180 pounds. If I graph 180 and I find the point of intersection of these two curves, The point of intersection is at an x value of 0.35. If that person's going to go mountain climbing, they want to make sure their rope has that diameter or more. You wouldn't, right? You wouldn't risk it and say, well, I'm going to get 0.35 inch diameter rope because the math says I'll be safe, right? One little stumble and you put a bit of extra weight on it because of physics and it breaks. Do you get the idea here? All right. On page 496, I mean, I say all here. I don't care. We got a little less than a half hour here. It's the Friday before your Christmas break. I want you to put in some work and get some practice here. Are you about to tell me that's not what's on there?
No, I was going to